Good morning, future presidents. Yeah. Good morning, future presidents. That's better. Okay, now I got your attention. So, two quick announcements. First, there is a practice midterm on B-Space under resources. Find it, take it, use it, okay? It's, of course, the questions aren't the same as the real midterm, but the format is identical and the content is pretty much identical. So this is a pretty good example of what your actual midterm is going to be. I suggest you take it timed because when we take the midterm in class, you're only going to have the class period to do it. I am not putting the answers up. At least not right away, quite on purpose, because I want you guys to actually think about the questions instead of just looking at the answers. And that's partly what your discussion sections are for, to go over things that you don't quite understand. So use your GSIs, you're paying for them, so get the most out of them. Okay, so today, I'll have my normal office hour after class, but I have to run off to a meeting at 11:30, so we'll cut it a little bit short. But discussions in office hours have been really good for the last couple of weeks. So I definitely encourage people to come if you can make them. If you can't make mine, make the other GSI office hours. Okay, so today we are covering the last topic that is going to be on your first midterm, and that is uniform circular motion. Okay, this is a special case where we're just applying the same Newton's laws that we have looked at so far, but in a special form of motion. So that's motion of an object in a circle moving at a constant speed. So this is a case when an object moves in a circle. At a constant speed. Okay, so there is nothing new in terms of Newton's laws for this, but the motion itself is a little subtle, and it takes a little bit of work to get your intuition down on that. So we're going to spend today working on uniform circular motion. So here is my object, so the ball and the string, right? And I'm just going to spin it around in a circle. So I'm spinning it at a constant speed. So it's moving in a circle motion. Okay, the speed is constantly changing. The speed is not changing. The magnitude of the speed is not changing. But a key point is that the velocity is changing. Not because it's changing magnitude, but because it's changing direction. The fact that the velocity is changing means that it has to have an acceleration, which means there's a force acting on it. Okay? And that's what we're going to study today, motion in a circle like that, and what the forces are that create circular motion. So let's draw that, that mass on the string as if we're looking down from above. So we're up on the ceiling looking downwards. Okay, so we've got our circle here. The object, the circle has a radius. Okay. And if we just look at the mass as it's moving around in that circle, then let's draw it at a few positions. There's its velocity at this point. It's moving tangent to that circle. So it's going up, so then it's bending around. At this point, the velocity is directed off to the left. At this point, the velocity is directed downwards on this board. I drew that much longer. I shouldn't have. This is moving at a constant speed, so the magnitude of that velocity isn't changing, but the direction is constantly changing. Okay, and then it comes back and repeats. So that is the direction of the velocity. So let's draw V on that. So we know that is the velocity vector at each point. Okay, so now the key point is that the velocity is constantly changing direction. when this object is moving around in a circle. It's not changing magnitude, but it is constantly changing direction, which means that it's being accelerated. The fact that it's being accelerated means there must be a force acting on it that is moving it in that circle. Okay, so let's look at a velocity vector for just a second. Here is our velocity vector, say at this point on the circle. And let's just think about the different directions that acceleration can be and how those would affect the velocity at that point. Okay? So the one we usually think about is an acceleration along the direction of motion. So if we have acceleration along that direction, okay, this acceleration would increase the speed. So that acceleration would speed it up, but it would stay in the same direction. So it wouldn't be changing the direction of the velocity. It would just be increasing the magnitude, okay? So increasing the speed. Okay, likewise, if the acceleration were directed opposite the direction, okay, we're also familiar with this one. This would decrease the speed. But it still stays in the same direction. It might eventually turn it around so it's moving negatively, so backwards, but it's not changing that velocity left or right. Okay? It's just slowing down the magnitude, decreasing the magnitude of the velocity vector. Okay, so those are if the accelerations are parallel to the velocity, but it doesn't have to be parallel. It can be perpendicular. So let's look at acceleration in this direction. Okay. So if this is the acceleration, okay, that is not directed either along or against the direction of the velocity. So it is not changing the magnitude of the velocity. Okay? All this acceleration would be pulling that velocity vector off to the right, which means it's just turning it, it's rotating it. So an acceleration which is perpendicular to the velocity has the effects of, this one would turn it to the right. Okay, but there would be no change in the speed. So this would not change the magnitude of that velocity vector. Okay? It would only change the direction of it. And likewise, if the acceleration were going off to the left like this, that acceleration would turn the velocity to the left, and there'd be no change in the speed. Okay, so let's go back to our drawing over here of this mass that's moving around in a circle. Okay? We already know when it's undergoing uniform circular motion, we're looking at the case where the speed is not changing, but the direction is constantly changing. Okay? So the accelerations we can have that change the direction but not the speed are always perpendicular to the velocity. Okay? So if we go back and look in this picture, when we have the velocity that's directed in this direction, okay, we know, right, that it's turning to the left, which means at this point the acceleration must be directed inwards towards the center of the circle. The acceleration at that point is just having the effect of turning that velocity but not of changing its magnitude. Okay? Now, if the acceleration were always directed off to the left, right, eventually when we got to this point, that acceleration would be increasing the magnitude and not the changing the direction. It would just speed up. Right? But that's not the case of the motion. This thing is always changing direction, which means that the acceleration is always perpendicular to the direction of motion. So that means when it's up here, the acceleration is directed inwards towards the center. When we're over here on this side, the acceleration has to be directed inwards as well, but it's the opposite direction of when it's over there. And finally, when we're down here, the acceleration must be directed inwards as well. Okay. So key point, When you have uniform circular motion, the object is always accelerating, but the acceleration always is directed towards the center of the circle of motion. So we have a name for an acceleration like that. It's called the centripetal acceleration. Okay, so centripetal acceleration is always directed towards the center of the circle. Okay, and the fact that it's always directed towards the center of the circle means that it keeps an object, whatever object it's acting on, keeps the object moving in a circle or moving in circular motion. Okay, so we know accelerations are like velocities. They're vectors, right? Accelerations have a magnitude and they have a direction. Okay? So let's try to figure out, at least a little bit intuitively, what the magnitude of the acceleration has to be in order to keep this object, which moving with some velocity v, it's got some radius. Okay? What magnitude of acceleration do we need to keep this thing moving in a circle? Okay, let's try to figure that out. We already know the direction of the acceleration, right? By definition, it's always going to be directed towards the center of the circle. So that's good. We have half of the acceleration down, but now we need to know what the magnitude of it is. Okay? So let's try to intuitively figure out what the magnitude is going to be. Okay, we could. It's actually a little complicated to derive this using calculus, which we're not going to use. So, but I think we can get an intuitive feel for why the magnitude of this acceleration is what it is. So let's make, and this isn't obvious, but let's make 3 points to understand maybe what the magnitude of this acceleration is. The first is that I think we can all understand intuitively that if you've got a velocity vector and you're trying to change its direction, okay, then let me draw that over here. So if you've got a velocity vector and you want to change its direction, you need an acceleration that's perpendicular to it. And I think it's pretty obvious intuitively that if you have a larger velocity vector, you're going to need a larger acceleration in order to turn it, right? If the velocity is very large and the acceleration is very small, it's not going to turn it much at all. Okay? So you need a larger acceleration to turn a larger velocity. Okay, so let's write that down in words over here. A larger velocity requires a larger acceleration. To change its direction. Okay, so that tells us that we probably have a factor where the acceleration, we're going to call this little r for the centripetal acceleration. We'll formalize this in just a second. Probably is at least proportional to the velocity, right? If you double the velocity, you probably need at least twice the acceleration in order to turn it same direction. Okay, so that's not the end of the velocity story, because let's think about that mass moving in a circle. So there's the circle. Here's our mass. Okay, I've got that string that's attached to it, so it's moving around with that radius. Okay, let's think about the time it takes to go around. Okay, so if I do this really slowly, right? This takes about 1,000. This is about a second going around, right? Okay, so if I speed it up, going much faster, then the fact I've increased the velocity means that it's actually changing its direction much faster as well, right? Just because the amount of time it takes to go in a circle is smaller and smaller. Okay? So that's a little bit different from the effect that I was just talking about. This one is just the fact that the velocity is larger means the acceleration has to be larger to turn it. You need a bigger acceleration in order to actually start getting noticeable motion. But this is a second effect. It is that the larger the velocity is, okay, so if we increase the velocity that this is going around in, the shorter amount of time that the acceleration has to turn it. Okay? So this one's just saying, this side over here was just saying that we need a larger acceleration in general to have effect on the velocity. This one is saying we also need a larger acceleration just because the amount of time we have to change the velocity and keep it moving in a circle is shorter. Okay, so that is actually a second component that comes in over here, and let's write it down. So the greater the speed, the more rapidly the acceleration, the direction must change. Okay, so a larger acceleration is required. Okay, this is another effect of the velocity. So these two are, if you think about it carefully, are actually independent of each other, and that means that the centripetal acceleration probably has another factor of the velocity that comes into it of this, okay? Which means that it has to go not just as the, it doesn't have to increase just as the speed increases, but it has to go as the square of the speed because you've got two separate effects coming in for that, okay? And the third one is, has to deal with the fact that there's a radius, right? So the third effect comes from the fact that that ball is moving with a radius, right? And if I have a very long radius here that it's moving in a circle, if I can do it at the same speed, I'll try to do it at the same speed. If I can do it at the same speed, then the longer that radius is, the longer time it has to turn, right? But conversely, the shorter that radius is, even if it's at the same speed, try to keep it the same speed, the fact that it's moving in a smaller circle means that it has to change direction much faster. Okay? So that means the shorter the radius is, the higher the acceleration has to be to make it turn faster. Okay? Which means that we expect there is a radial effect on this velocity, on this acceleration. Let me write that down. The smaller the radius of curvature, that's just the radius of the circle, but I haven't used that term yet, so let me underline it. The smaller the radius of curvature, that's just the radius of the circular motion, the more rapidly the direction changes. For that, and this is for a given speed, and so larger acceleration is required. Okay, so if we're thinking about how the centripetal acceleration depends on radius, it can't be proportional to the radius because in that case it would increase as the radius increases. Okay? The easiest way to think of this is if it goes as the inverse of the radius. So as the radius gets larger, as this term on the bottom gets larger, the acceleration gets smaller, or vice versa, as the radius gets smaller, the acceleration gets larger. Okay, so if we put those three factors together, let's combine those three. We've got two factors of velocity and the inversely proportional to the radius. Then our guess for what the centripetal acceleration looks like is that the centripetal acceleration, so that acceleration that's keeping it moving, acceleration in a circle, going to be equal to the square of the speed. So combining those two velocity factors divided by the radius of the circle. Okay. Usually we give centripetal acceleration a sub r, so the acceleration directed along the radius, that's what we use a sub r for, is equal to the square of the speed divided by the radius symbolically. Okay, and our reasoning is of course correct, or I wouldn't have went through it. That is the value of the centripetal acceleration that keeps an object moving in a circle. So when you have an object that's undergoing a circular motion, if it's got some speed v and it's moving in a radius r, okay, then that means that there is a centripetal acceleration keeping it moving in that circle. And that centripetal acceleration has to be equal to the square of this speed divided by the radius. Okay. So, of course, that means if you double the speed that's moving in a circle, to make it go around twice as fast, then you're requiring 4 times the acceleration to do that, right? Okay, so acceleration. So we've just been talking about this acceleration in terms of how it affects the velocity, but now let's think about it physically. We know that accelerations don't just happen. Newton's laws, especially Newton's second law, tells us that if there's an acceleration, if an object is accelerating, there must be a force that is acting on that object, which is providing the acceleration. Okay, so if we have uniform circular motion, that means we have an acceleration on the object, which means there must be a force that's exerting that acceleration. And we just call that, you can imagine, we've already called the acceleration centripetal acceleration. So we call the force centripetal force. Okay, and we also give that the symbol usually F sub r, because that is the force directed along the radial direction towards the center of the circle. And that is just going to be equal to the mass times the centripetal acceleration. That's just Newton's second law. The force is equal to the mass times the acceleration. It's just in this case the acceleration is the centripetal acceleration, and that's equal to the mass times the speed squared over radius. Okay? I'm giving you these formulas, but I don't expect you to memorize the formulas, but to understand intuitively what they are implying about the forces and the directions of the accelerations. Okay. So this is a force that is always directed towards the center of the circle. In the case when the ball is spinning on the string, that force is being provided by the tension in the string. And it's the tension in the string that is always directed towards the center of the circle, and it's always pulling it, it's always changing the direction of the velocity. Okay, so a very important point here, and a caution. Centripetal force is not a new type of force. There is not some fundamental force of nature called the centripetal force. Okay? Centripetal force is always a force that we've already seen. It's gravity, it's a normal force, it's a tension. When we call it a centripetal force, we're just talking about what direction it's pointed in. Okay? It's just pointed towards the center of the circle. Okay? It's not a magical new force. It'd be kind of cool if there were a new force that we discovered, but it's not. Okay? It's just the direction. It's whatever, it's the direction, it's the force that is directed towards the center of the circle. And we call that component the centripetal force because that's responsible for the object moving in a circle. So let me reiterate that with a few little pictures here. Here is our ball moving in a circle on a string. There's a string. So there is the ball moving with its speed. Okay. And in this case, and it's got the radius. In this case, for the ball on the string, I should have drew that over there. That's okay. Okay, so that's our ball on the string. The centripetal force, just call it F sum r here. Centripetal force, in this case, is equal to the tension in the string. There is not a new force, new type of force, which is centripetal force. It's just that the tension in the string is always directed towards the center. So the tension in the string is providing the centripetal force in this case. Okay, here is the Earth and all of its splendor. Okay. Here is a little satellite orbiting around the Earth, uniform circular motion. So this is a satellite in orbit. Orbit. There's our satellite. It's got a velocity, it's got a mass, it's moving in a circular orbit, which means it's got a centripetal acceleration. The centripetal force in this case is just its weight, mg. There's not a new type of force providing the centripetal force. It's just that the gravity is acting always towards the center of the circle. So in this case, the centripetal force is equal to gravity. Same type of circular motion, different force providing the centripetal force. And the last one I draw, which we're going to go into in more detail immediately, is a roller coaster. This is a loop-the-loop on a roller coaster. Okay, so here is the roller coaster car. It's moving in a circle with some radius. It's got a mass. It's got a speed. It's undergoing circular motion there. And there are actually two forces acting on it, which we're going to talk about. But the primary force here is the normal force. I hope you guys can see that. That's a normal force acting, pushing down on the wheels there, keeping that in circular motion. Right? We also know, and I'll put it plus gravity, because we also know that the weight is acting downwards on that. Okay, so for the roller coaster, the normal force, the centripetal force is going to be equal to the normal force, which is the track pushing on the car, plus the effects of gravity. Okay, this one's a little bit more complicated. So we're going to talk about this one in detail right away. Before we start talking about the roller coaster in detail, are there any questions on what we've talked about so far? It's all obvious, huh? Yeah, over here. So the difference between 1, 2 in the justification. So the difference between those is that well, let me say it one more time. And if it's not clear, then don't worry about it too much. So the difference is that if we've got a large velocity, right? So think about it, if you double the velocity, then if you want to turn it by some given amount, you're going to have to double the acceleration, okay? Say to turn it by some amount over a given time, right? So let's say we're going in a circle once a second, right? If we double the velocity, then we're going to have to double the acceleration in order to get that to move. So the second case is that when we do double the velocity, it's no longer going around once a second. It's going around twice a second. And the fact that it's moving faster means that we also have to increase the acceleration because it has to not just turn a bigger velocity, but it's got to turn it faster. So the effect is that, remember, the acceleration is a change in velocity. And so if it's a bigger velocity, you need a bigger acceleration to change it. But the fact that it's going in a circle and it's going faster in a circle means you need to change it faster. So there's two components of velocity comes in. So that is not an obvious conclusion. So it takes a lot of time to think about that and to mull on that. So yeah. So hopefully that clarified that a little bit. So. Okay. Any other questions? Yes. Okay, so let me see. You're asking, if this is MAR here? Oh, in my examples. Let's see. Oh, sorry, yeah, this is mg. So this is the weight. So that's the gravity acting on this. So there's two forces acting on that. So we're going to go in that one in detail right now. So let's move on to that if there's no other quick questions. So. Okay, so let's look at our roller coaster in more detail. I always seem to migrate the erasers to one side of the room for some reason. Okay, so we're going to look at the loop-the-loop on the roller coaster. Okay, so before we go into detail, let's just think about that intuitively for a roller coaster. I think we know intuitively that if we've got a car that is approaching a loop-the-loop in the track, then the car has to have a certain amount of speed in order to make that. And if it goes too slow, it's not going to make it. Okay, so we want to look and see if we can understand why it needs a certain speed in order to go around that loop. Okay? And if it's going too slowly, then we know it's just going to fall. Okay, so before I start playing with that, let's draw the picture of it. So here is, let me draw a big picture of this. There is our track. It's got some radius, r, and we are going to look at the car on that track at actually two different positions. So let's draw the car as it's coming into the track here. It's moving with some speed v. And let's draw the car at the top when it's moving off to the left. Okay? We know from conservation of energy that speed is going to be slower than this speed, but let's not worry about that here right now. Let's just say it's got some speed at this point, it's got some speed at that point, and let's look at the forces and the accelerations acting on it. So let's call this point at the bottom point A, and this point at the top point B. And let's think about the forces that are acting on this car. There are two forces that we need to take into account. There is the weight of the car. So that's the gravitational force, and we know the gravitational force is always directed downwards. Okay? And there is the normal force, or the support force. Of the track. And that one, remember, normal force is always directed perpendicular to the surface. So when the car is sitting on the track, the normal force down here at the bottom, the normal force must be directed upwards. And as it goes around the track, the normal force is always perpendicular. Okay? So it's going to be changing direction as the car moves. Okay, so let's look at the forces on the car, those two positions. And let's think about the accelerations. Okay, so let's start off at the bottom point. Okay, so we're at point A here, and let's draw this car again. There is the car moving along the bottom of the track. It's got some speed going off towards the right. It has two forces acting on it. It's got its weight acting downwards. Okay. And it's got the normal force of the track holding it up. So it's directed in the upwards direction. But now, I didn't draw that on that. Let's draw that up there so it's clear where the accelerations are for each point. Okay, here it is moving around in a circle, right? So that means at this point, the centripetal acceleration must be directed upwards towards the center. And at this point, the centripetal acceleration must be pointed downwards towards the center. Okay, so let's go back to this. And let's draw the acceleration upwards. Okay. So at that bottom point, it's accelerating upwards. That acceleration is keeping it moving in the circular motion. Okay. The fact that the acceleration is upwards means that the net centripetal force on the car at that point must be upwards. Okay. Now the net force, the centripetal force, remember, is not its own force. It's the actual physical forces that are acting on the car in that direction, right? And we've got two, right? We've got the normal force that's acting upwards, and we've got the gravitational force that's acting downwards. So those are the two forces. In this case, the net force is upwards because the acceleration is upwards, which tells us that the normal force has to be bigger than the weight. Okay, so the fact that this car at the bottom is moving in this circle means that the track has to push up on it with more force than if it were just sitting there. Because the track isn't just holding and supporting its weight, it's actually accelerating it up towards the center of that circle. Okay? So it needs a stronger normal force than just the weight of the car. Okay? And we know what that is. We know what these are. This is the net force acting on it. That has to be equal to mv squared over r, the mass of the car times its acceleration. So this is just force equals mass times acceleration, Newton's law, where the net force is going to be the difference between the normal force pushing it up and the weight pulling it down. And we know the acceleration is v squared over r, the centripetal acceleration. Okay, don't forget too much about the equation. I just want to think about it intuitively, what's going on here, right? So I just told you that the, remember, so if this car was just sitting here on the bottom, right, perfectly at rest, then the normal force would just be equal to its weight because they're balanced and it's not accelerating. The fact that it's moving, right, at that bottom point means that the normal force, there has to be a net force accelerating it, which means the normal force is larger than it would be otherwise. So the track has to push up on it larger than the weight. So that's pretty important when you're designing a track, right? Because you need to not just support the weight of the car and the people, but you need to support the centripetal force that keeps them moving in a circle. Otherwise, the track is going to break when that fast car comes and hits it. Okay, so, and the flip side of that is this, as the car goes slower and slower, right? If we're doing this really, really slowly, so slow that this is almost at rest, then the normal force is just equal to the weight, right? It's basically just supporting the car, okay? Conversely, the faster it goes, faster and faster it goes, the more normal force that we need in order to keep it moving in that motion, okay? Now, the tricky part, let's look at the top of the car when it's at the top of the track. This is a little bit more subtle. It's not that much more difficult if you understand the bottom there. So let's draw this at the top. So this is point B at the top. Here's our track. Here's our car. Now it's suspended there upside down. Okay. But it's still moving with some speed v. Okay, it's got two forces acting on it. It has got its weight, mg, pulling it downwards, so that's a gravitational force. It has the normal force of the track, but in this case, it's on the bottom side of the track, which means the normal force is directed downwards. Okay. It's still moving in a circle, which means that it has a centripetal acceleration in the downwards direction, okay, which of course means that the net force, centripetal force, is directed downwards. Okay. Now, these are acting in the same direction, the normal force plus the weight. So the centripetal force in this case is not the difference between the two, but the sum of the two. And that is going to be equal to the mass times the centripetal acceleration, mv squared over r. Okay, so the combination of the normal force plus the weight, they're both acting downwards towards the center of that circle. So they're both acting, contributing to the centripetal force, which is keeping this thing moving in a circle. Okay, so now the key is this. Think about what happens when that car comes up and it's moving slower and slower. Okay? So we're going to start this off moving fast. Oh. Ouch. Catastrophe at the carnival. Okay, so you see it had no problem going around that. Okay, that's because it had enough speed. Let's imagine what happens as it slows down, right? As the speed gets smaller and smaller. If we started off, up here so it doesn't have as much speed, then it doesn't make it around there, right? So let's think about what's happening in that case. What we're changing when we decrease the speed here is we're dropping the acceleration, right, that we need to go around that circle. When this term gets smaller, this is still equal to the net forces acting on it. Okay? But those two forces, there's the normal force and there's the weight, right? And the weight isn't changing. The weight of that car does not care how fast it's going around that track. The force that's changing that depends on speed is the normal force. Okay? So as you decrease the speed, the normal force drops. Okay? Conversely, as we increase the speed, the normal force gets larger and larger. So the faster we try to go around this curve, it's going to take more normal force for that track to hold it back. So that's intuitively obvious, right? The faster it goes, that track is going to have to push down on it harder to keep it moving in a circle. The slower it goes, though, the less and less that normal force is. If we go slow enough, then the normal force goes to 0. Okay? If we decrease that speed slower and slower, gravity isn't changing, but the normal force is dropping. You need less and less normal force in order to hold that car on the track. Okay? If you get to the point where the normal force is 0, okay, remember normal force comes from two objects pushing together. Okay? If the normal force goes to 0, then that means the car has lost contact with the track and it falls. Okay. So at the top of the track, we have to maintain some minimum speed such as the mass times the centrifugal acceleration is greater than the gravitational force acting on that car in order to keep this normal force non-zero. That means that we're keeping it in contact. If it goes to zero, then we lose contact, which means that car is falling. Another way to think about that is that the gravitational force at the top is too strong in order to just maintain the circular motion. It actually starts at accelerating downwards as well. Okay, now let's look at this demo again, and we can do this for real this time. There are 3 different types of masses here. They are all circular masses. Their difference is that they have different moments of inertia. So this is a little, rotational mass. That's what we're calling it in this class. They have different rotational mass. The one with the smallest rotational mass is the solid sphere. So this one has its mass distributed most closely to the center, which means that it accelerates faster down ramps, okay, than one that has a larger rotational mass. This one has no problems making it around there. Ooh, I'll be glad when we're not dealing with balls anymore. I seem to have issues. Okay, so the next largest rotational mass is a solid disk. And this has a larger rotational mass than that solid sphere because more mass is distributed further away from the center, which means that it's harder to accelerate, which means it doesn't have as much speed when it goes down that thing. Okay, but it still made it. That's good. Okay, here is this hollow cylinder. It has all of its mass distributed around the radius. So that means it has the largest rotational mass of these 3, which means it's harder to accelerate down down this ramp, which means it has a smaller velocity. And, great, can you grab that? No, get it. Oh, thanks. Good. So smaller velocity when it hits that loop, okay, which means it doesn't have enough velocity to make it around the top. So when it gets up to the top, its normal force has gone to 0, and it loses contact with the loop, with the track and falls. Okay. So, okay, let's do some other demos of the normal force. Okay, this is an experiment you all tried when you were kids. Now we can understand it. Okay, I got a bucket. It's full of water. Okay, I'm going to spin it in a circle, just like the loop-de-loop, okay, the roller coaster. So we know if I spin it fast enough, when it's up at the top, let me draw it before I. Here's the bucket. Here's the water at the top. It's moving with some speed v. Okay? As long as that speed is fast enough, they're still going to maintain a normal force pushing that water down, okay? Which means it stays in contact with that bucket. Okay? And so as long as I do the speed fast enough, that force pushing it downwards is going to be required to keep it moving in a circle, okay? Not to make it fall. Okay? So if I do this fast enough, are you scared, Heather? You trust me? Yeah, that's probably unwarranted. Okay, so if I do this fast enough, right, there's no problems going around. If I do it really fast, so the faster I do it, right, 0 problems. Always got enough normal force. If I hit myself with this, it's going to be a disaster. Okay, so let me slow it down. Okay. The problem is if I go too slow, right? So as I go slower, that normal force is going to drop at the top to the point where it's 0. Are you ready? Okay, I'm not going to do that. I know from doing the numbers on there that the slowest I can rotate this is about 2 seconds to go all the way around. So 1 1,000, 2 1,000. So 1 1,000, 2 1,000. Okay. Actually, this is a little longer. I can probably get away with that more. Ooh, it almost fell. Okay, you guys can play with this you can play with this in the dorms. I'll give you the right to do this in the hallways, okay? And figure out what's the slowest you can turn that when the normal force disappears, okay? So let's think about that, though, what's going on. The fact that it's moving in a circle, okay, means that the forces are still there. It's still got its weight pulling it down, right? But those forces, remember, the forces change the direction of the velocity. The forces add an acceleration. And the fact that it's already got a velocity moving to the side means that force is just making it move in a circle. It's not pulling it straight down. If that velocity disappears, right, it's just going to fall straight down. It's still accelerating downwards. It's just that the velocity keeps it moving in a circle instead of falling directly downwards. Okay? So let's do 2 more examples of that. This is my cowboy experiment. This is just a chain. It's supposed to be like a lasso, but this is a chain. Okay. Let me straighten this up a little bit. So this is called a chain lariat. And if I do this slowly enough, we can get this whole chain moving in uniform circular motion. There we go. Okay, that I gotta be a little careful there, it's going crazy. Okay, so that's moving in uniform circular motion. The entire chain, each segment of that chain, each link of that chain is moving around in a circle. There is a rope that's connecting it that I'm twisting it with, but that's not what's providing the force. The force on each link is being provided by its neighbors, right? Got to be a little careful here. So each neighboring link is pulling on the link in the middle, okay, and it's pulling it towards the center of the circle, and it's allowing it to move in this central motion. So let me draw that. Okay, let me draw that picture as best I can. Let me just draw 3 links on that chain. So there are 3 links, and that chain extends around into a circle. Okay. So when it's moving in a circle, that link is moving with some velocity. Okay. It's got an acceleration towards the middle, just like any mass does moving in the center, but that means there's a real force that's acting on it. The only thing that chain is in contact with, that link of the chain, are the neighbors, right? So this link of chain is trying to pull it to the right. That link of chain is trying to pull it towards the left. So those are just tensions. Same thing for a rope, if I were doing that with a rope. Okay. And the thing is, those tensions can actually be really high depending on how fast it goes, but they're not perfectly balanced because they're directed a little bit downwards. So each link is kind of pulling it downwards just a little bit. Okay. So they mostly balance out each other, except for a little bit of the component of each one, which is directed towards the center, which is providing that centrifugal acceleration. And here is another example of that. Okay. Another chain. So perfectly floppy. But that's because I haven't introduced any tension in it yet. Let me introduce a little tension in that chain by giving it some circular motion. Okay, so this is speeding up. Okay, let's see. Can you, yeah, thanks, Wei, that's perfect. Okay, so now this chain has a lot of circular motion. Okay. So let's give it, okay. So as long as that chain was spinning fast enough, thank you. As long as it was spinning fast enough, the tension in the chain was actually going to keeping it moving in a circle instead of making it collapse, right? It's because I had so much velocity that the force and that inside the chain itself is just going to change the direction of the velocity that I've given it instead of making it collapse. I'll do that one more time. Okay, uniform circular motion. Thanks. I'll do it over and over again. You're being so good. Thanks. I'm picking it up. Okay, so let's talk about another example. Are there let's see. Are there any questions so far about what we've covered? Good. You guys got your circular motion intuition all together, huh? Let's see, where's it at? Oh, there we go. Yeah. So that is that's a great question. So his question was that Newton's third law says there's always an action-reaction. So in this case, when the roller coaster is going around the track, the normal force of the track is pushing down on the car, right? So the reaction to that is the car, of course, is pushing back on the track. Okay? And so those are the action-reaction pairs, the track pushing down on the car. So the track is exerting that normal force on the car, but the car is also exerting the equal force backwards. So that's important to know when you're designing this track, right? Because that track has to be strong enough in order to take that force. And so how thick a steel you use here, or and how much support you put on the track when it goes around the top will depend on how fast you're making that car move around that circle. And the faster you make it go around the circle, the more reaction force you're going to have on that car on the track, which means the track is going to have to be stronger. Does that make sense? Yeah, great. Okay, so let's talk about another example, which is a very important example, which are highway curves. So when you go around a curve in a highway, you might not know it, but you are usually doing some sort of circular motion. If you're going around at a constant speed, you're doing uniform circular motion. So let's draw a picture of that so we all know what I'm talking about. Okay, so highway curves. Okay, so imagine here you are traveling along the road and there is a curve in the road. Here's your car, you're moving along with some speed, okay? And you're going to hit that curve and you're going to be turning off to the left. So that curve, at least that segment of the curve, is a part of a circle, which means when you're going around that curve, you are undergoing uniform circular motion, at least for that quarter of a circle. So you have a radius of motion there. Let's draw the car. So when the car is actually on the curve, its direction is changing, which means it has a centripetal acceleration. And we know the relationship. The centripetal acceleration is just the square of the speed divided by the radius. Okay. Let's draw that from the perspective of the car now. So let's imagine you're in the car behind that car. Okay? So you're watching it as it goes around that curve. So here is the scene from the back of the car. So here's the steering wheel, so we know the orientation. There is the driver of the car, and here's the passenger. Okay, so from the back. So that means that this car is driving into the board this direction, right? And it's turning around that direction, so that means the acceleration is directed off to the left, okay? So the same direction as here. It's just now we're looking at it from the ground level as the car moves. So you have to picture this car is driving into the board, so away from you guys, okay? So let's look at the forces on that car. We know that that car has a weight pulling it downwards. We know that it has a normal force, the road, which is pushing upwards on it, which is supporting the car. But it's accelerating in that direction. there has to be a force acting on it in that direction for it to accelerate in that direction. Any idea what that is? It's the magic force, friction. Thank you. So we have to have a frictional force between the tires and the road, which is providing the centripetal acceleration in this case. That is bad. That is really bad. So there's a lot of reasons that's bad. One of them is, in this case, we're imagining here's the tires, right? So if the tires are just moving in a straight line here, they're not slipping left and right. So this is static friction. So this means that we're relying on a frictional force to go around that curve. The reason that's bad is, for one thing, that's static friction. We know that static friction is always greater than slipping friction. So that means if that car starts to slide, suddenly that frictional force is going to drop, and suddenly it doesn't have as much force putting it around the circle. Okay? That means it's going to go over the edge, right? It's not going to go around the curve. Okay? Other reasons this is bad is because of weather. Okay? The frictional force is going to drop if it's icy or if it's rainy. If there's oil on the roads, we all know what happens whenever we get the first rain, especially out here in California where you have really dry seasons. All the oil on the road bubbles up and it gets really slippery. Okay? We don't want to have to rely on friction in order to go around curves. Okay? The other thing is that now think about speeders, right? If you double the speed you go around that curve, your acceleration goes up by a factor of 4, which means you need 4 times the force in order to go around that curve. So if you're relying on friction to move you around that curve, then you're probably going to be in pretty bad shape if you go too fast. Okay, so that's not good. So that's not how we design highway curves, quite on purpose. We don't want to rely on friction to go around that. So curves are banked. To avoid friction altogether. Okay, so let me draw a picture of what that looks like. Here's the same car from the back, but now for a real highway curve, it would not look like a flat road like that. I've exaggerated here, but the curve would look like this. So there's the driver, there's the passenger. Okay. So it's tilted at an angle like that. And the reason is we still have a centripetal acceleration in this direction. We still got the same forces, but gravity is always acting downwards. But now the normal force has been tilted, right? So the normal force is tilted up, perpendicular to that surface. And that means there is a horizontal component of this normal force directed towards the center. So these are not perfectly balanced. Okay? Okay, when you add them together, you're left with a residual little force pushing inwards, because the normal force is pushing towards the left in this case. And it's that horizontal component of the normal force that provides the centripetal force. So that means that we are not relying at all on friction. We're just relying on the fact that that curve is banked and the normal force has a little component going inwards. Now, there are some complications to that. First off is that these highway curves are always designed for specific speeds. So when you see a sign on a curve that says 50 kilometers per hour, okay, that's not just because they don't think you're a good driver. That's because they designed this curve so that a car going around it at 50 kilometers per hour needs 0 friction in order to go around that curve. Okay? That is the design speed for this curve. They picked the radius of the curve, and they picked the bank of the curve so that a car going around it at 50 kilometers per hour only needs the normal force of the road. If the car is going faster than 50 kilometers per hour, then there has to be an additional force that's providing that extra push to the left, which means there has to be a frictional force with the road pushing downwards. So if you're going faster than the design speed, then once again you are relying on friction. Okay? If you're going slower than the design speed, then that means that the normal force is too much, which means that you're relying on frictional force in the opposite direction, okay, to balance out. So it's actually good to go around the curve exactly at the speed that it claims. If you go any slower, you're requiring frictional force as well. The caveat to that is, remember that the acceleration goes as a square of the speed. So if you go around that curve twice as fast, then you require 4 times as much force in order to keep you going in circular motion, which means that the frictional force that is required if you're speeding around that curve is much larger than the frictional force required if you're going slowly around the curve. Okay, so it is better to go slower around curves than faster around curves. Let me make that clear. Okay? So, but both of them actually require frictional force to keep you in. Now you might think, sometimes some racetracks, right, have really steep banks on them. And you see race cars going around really shallow curves. You might think, wow, that'd be really cool. We did that on Highway 80, right? Had really steep curves, that would be fun. There are limits on that, which is depending on how steeply they make those curves. So the higher banked it is, it means the smaller the radius is for the curve. Okay, so imagine that they redesign Highway 80 with a really steep bank on it so that you can go around those curves really sharply, right? So the problem with doing those really steep banks is that eventually that traffic's going to stop, right? If it stops, especially if it's icy or wet out, you don't want all the cars sliding down the bank because the road is too slippery, right? So you do have to design it so that when cars are stopped on the bank, on the highway curve, they're not slipping down the bank. So that means that you have to design basically the inclination so that even in the worst conditions, if it's really icy, a car that's stopped on the road isn't going to go sliding down it, right? So that sets the radius. Typical radius for highway curves are around 1 kilometer or so. But when you see those signs around a curve, that sign is the design speed, okay, which means you're not relying on any friction to go around that curve. Okay, so in the last 10 minutes, I just want to talk about the passengers in this car. Okay. The passengers in this car, say that you and your friend are in that car and you start going around a curve. As you go around that curve, 2 things are happening. First off, you are accelerating, right? So the car is accelerating in a circle, but the fact that the car is accelerating in a circle means that you are also accelerating in a circle. Okay? And that means when you are in that car, you are in an accelerating frame of reference. Right? You're no longer in an inertial frame of reference or a non-accelerating frame of reference. This is your frame of reference, the car. And you're in a frame of reference which is accelerating because it's going around a curve. Okay, so we've already talked a little bit about what happens to our perception of forces and such when you're in an accelerating frame of reference, and that's that we can measure real forces acting on us. So for example, we talked about the elevator, right? If you're standing in an elevator and the elevator is accelerating upwards, that means it's accelerating, the fact that it's accelerating upwards means that you have more normal force acting on your feet, which means you feel like you have a larger gravitational force acting on you. Even though you don't, your real weight has not changed at all. Your apparent weight, or your fictitious weight, apparent weight is probably a better term, feels like it's increased because you are an accelerating frame of reference. Okay? Same thing in the car. We just have a different name for it. If you're in a passenger in that car, right? Here you are in that passenger seat. It's going around a curve. There's acceleration off in this direction. If you're in that car, you don't feel like you're accelerating. You just feel the forces that are acting on you. Okay? And what do you feel? You feel, well, there's weight that's pulling you down. There's the seat normal force that is pushing up on you. And if you're going fast enough, there can be, frictional force with the seat, right? Seat's pushing against your bottom, keeping you from sliding. And if you're going really fast, you can have the door, right? You can even have the normal force of the door pushing on you, right, to hold you, keep you moving in that circle. We all know that if you go around a curve fast enough, you'll feel the door pushing against you, pushing you around that circle. Okay, what do you perceive? So the fact that all these forces are accelerating you in this direction, in this frame of reference, it feels to you like something is pushing you out. Right? You don't feel like suddenly that door is pushing against you. What you feel is that something's pushing you against the door. Just like when the elevator accelerates upwards, you feel like gravity's increased and is pulling you downwards. Okay? So that is just an effect from your frame of reference, because your frame of reference is accelerating. Okay? So, but we have a name for that. It's we call that centrifugal force, which sounds an awful lot like centripetal force, unfortunately. Centrifugal. And that is the apparent force pushing you out. So that is the apparent force that's pushing you towards the outside when you're accelerating in a circle. Okay? There is no force there. It is absolutely not real. There's no force that is pushing you to the outside of the car. It's just your perception because you're in an accelerating frame of reference. Okay? Let's see, we have 5 minutes. Let me draw this. Let's see, can you bring up, actually, hold on 1 second. Okay. There have been proposals to use this, though, for some pretty cool things. One of them is creating fake gravity environments in space. In Star Trek, they have some magical field that creates gravity, but we know how to do it in a spaceship. We just sent that spaceship rotating. So let's imagine we have a big circular spaceship. And we're going to send that rotating in a circle. Then when we do that, if you imagine you are a passenger on that spaceship and you are standing on the edge of it, you are moving with a velocity. You have an acceleration towards the middle. That means there's a normal force on that spaceship that's holding you up for the floor. And to you, that looks like that's a centrifugal force pushing you down, and it looks like gravity, or it acts like gravity. So as long as you're standing on the outside edge of that, so you can imagine that other passengers would be standing like this as that thing rotates around, then there is a fake gravity environment in that. Now, we don't have to go to space to do that, fortunately. There's a really often poorly named space. Let's see, can we have the projector, please? Starship 2000. Let me turn these off. Okay, there is a rides at the circus that does this exactly, right? Sometimes they're called rotor rides. Sometimes they're called zero gravity rides, which is really a bad name because, in fact, they have higher gravity. I like the music on this, too. So these guys are in a big rotating cylinder, right? Which is providing a centrifugal force pushing them outwards, which looks exactly like fake gravity to them, pushing them towards the outside of this cylinder. They're in a big spaceship here. There's like thousands of videos like this on YouTube, by the way, so I thought this was the most entertaining. You can see that there at the end, that guy is getting brave. In theory, you can stand up on these, but it takes a lot of coordination. Okay, they're feeling a real force. It's a normal force that is keeping them moving in a circle, but to them, it feels like gravity is pulling them out towards the edge. Okay, that's it. So this is the end of the material that's on your midterm, by the way. So we will cover other material next week, but it won't be on your midterm.